So what we're going to do is we're going to look at differential equations. And we've actually done this to a certain extent already, but we're going to go into a much higher level than what we've done before. So first of all, you need to remember what a differential equation is. It's an equation that has a derivative in it, either y prime or dy dx. So in example 1, it says you want to solve the differential equation y prime equals 2x over y. Well, the first thing you need to recognize is y prime is also equivalent to dy dx. So if you have a y prime, you're going to want to rewrite it as dy dx. And when you're solving a differential equation, you're trying to solve it for y. So then what we do is you want to multiply both sides by y, and I'm going to multiply both sides by the dx. So this is going to give me, do you understand what I did? The y is down in the bottom, so I multiply by y. The dx is down in the bottom, so I multiply by dx to both sides of the equation. So now, what you do in 6.3, the nice thing is 6.2 and 6.3 go together very nicely. And so you're going to do this again, but we'll get more complicated with it. But it's called separating your variables. You want your y dy on one side and your x dx on the other side. Now, in order to solve this, the integral of a derivative undoes the derivative. So this is 1/2 y squared equals x squared plus c. I'm done. I don't need to do anything else. One thing they might do in the back of it, bless you, is if you multiply both sides by 2, do you understand that the arbitrary constant, it's still an arbitrary constant, it's just 2 times the previous row? So you can leave it as a c. We don't put 2c. It's just a different c, but it's still a c. And we're not going to go any further than this. If you have just a y to the first, we will put those by themselves. But if you get a y cubed, a y squared, anything ln of y, some of the ln y's we'll handle. But, you know, just do your best to try to get your y squared or y cubed alone. All right, so solving a differential equation means you get your y and dy on one side, your x dx on the other, and you integrate. Yeah.
So we can leave it squared and cubed.
Yes. Mm-hmm. And I'm actually okay if you leave it the 1/2, you know, like we're okay there. But if it's a y to the first, we'll go all the way to y equals. Okay, that's the only one I'm picky about. If y is y to the first, then we'll leave that one alone. All right, growth and decay models. It says in many applications, the rate of change of a variable y is proportional to the value of y. Okay, let's stop and let's really pick this apart. The rate of change, and we had trouble with this on the test, that extra credit. And so I want to make sure now that we're really, really clear. It says the rate of change of a variable y is dy, and see they're doing this with respect to time, so it's dy dt is proportional to the value of y. So this equals k times y. You remember direct variation was y equals ax or y equals kx in whatever algebra 2 or advanced math. Okay, so if it says you have a rate of change and it's proportional to something else, you're going to have it set up like this. dy dt equals k times y. Now watch this. I can, in fact, divide both sides by y, and I can multiply by the dt. And I want to show you this because this is going to explain what happens in the next box. Okay, dy dt equals k times y. I want to pull the y over to the other side. And the way you do that is you divide by y. And I can multiply by dt. Now watch this. If I go to integrate, this is ln the absolute value of y equals kt plus c. All right, again, do you see, if I integrate 1 over y dy is the natural log of absolute value of y. If I just have a constant, it's kt plus the arbitrary constant c. Now watch this. I can, in fact, solve this for y. This is why in chapter 5, we went from logarithmic to exponential form and exponential to logarithmic form. And we went back and forth. The natural log is a log base e. So if I were to go from this logarithmic form to exponential, it's going to look like this. This is e to the kt plus c power equals y. Okay, and I want you to pause and really think about it. So I went from logarithmic to exponential, that's e to the kt plus c power equals y. Now, I'm going to back up to algebra 1. Do you remember if you have a to the m times a to the n, that's a to the m plus n power. Remember this? Like if I had x squared times x cubed, we said that was x to the 5th, right? Way back to algebra 1. But watch this. This is like so cool. This is super, super cool. Watch this. I'm going to blow your minds. And I want to see if you can stay with me here. This is super cool. Okay. I've been having a fabulous math day today. I just thoroughly enjoyed myself. You guys, I pinch myself every day that I get to come and do this. I love this. I absolutely love it. And I'm not unrealistic. I don't expect you guys to love it like I do, but I expect you to find something that you can be passionate about and be passionate. But I love this. This is like so fun. So watch this. Do you guys get do you see it? That is that property. See it? I mean, I really, really need you to lean in and look at this. Look, if I had e to the kt times e to the c, we would have added them together. Now, e to the c is just some constant, right? That's like e to the 2 or e to the 3 or e to the 4. Watch this. This is going to go c e to the kt power. I know.
That goes wild. Oh my god. So you have to take it down from all those steps?
Yes. Okay, and so the good news is we're going to do this over and over and over again. But this is, oh my god.
I wish I was that happy about something in life.
This is so exciting. It's so cool. All right, so the rate of change of a variable y is proportional to the value of y. Well, you know, at least I can't be called boring. I'm weird, but I'm not boring. And I'm okay with that. Okay. All right, so let's look at the box, okay? Everybody got it? Yeah. So here's in general. If you have that y is a differentiable function of t such that y prime equals k times y, then y, and I worked this out for you, okay? So what's kind of nice, you can either rework it every time, or if you see that the rate of change of a variable is proportional to that variable, you can automatically write y equals c e to the kt. So you either memorize it or we figure it out. C is the initial value of y. K is called the proportionality constant. And I'll step out of the way in a moment. Exponential growth occurs if K is positive, and exponential decay occurs if K is negative. Yeah, that's right. So what's interesting is we're going to look at chemistry, we're going to look at biology, we're going to look at like radioactive elements, that have exponential decay. We'll also look at money. We'll look at money is exponential. But in biology, you might have, one of the things we're going to look at are fruit flies. They multiply exponentially. So we can look at how they can collect data and then write equations and make predictions on the data, which is cool. All right. Example 2 says the rate of change of y is proportional to y. So since we have it right there above, let's go ahead and write down then the general equation instead of reworking it is y equals ce to the kt. Now what's going to happen is they're going to give you at least one pair of numbers that go together, if not two pairs, because I have c and k are unknown. You see that? C and k are unknown. So what I'm going to do is I'm going to plug in y is 2, I don't know k, and t is 0. Okay, with my first ordered pair, you plug it in, and if you get t is 0, that's going to be super helpful. This is 2 equals ce to the 0, but what is e to the 0 power? 1. So c is 2. So now I've got y equals 2e to the kt power. So I still have something else that's unknown. So there's where a second ordered pair helps, because I can plug in the t is 2, the y is 4, then the only thing missing in this equation will be k. So this is 4 equals 2e to the k times 2 power. So now let's solve this. So this is 4 equals 2e to the 2k, divide by 2. Now in chapter 5, so it's very intentional how things go, because now if I want to solve this for an exponent, I need to take the natural log of both sides. So I'm going to get the natural log of 2 equals, and then you bring down the power. Okay, when you have an exponent is your variable. Okay, if you have an exponent is your variable, you need to take a log of both sides, and that allows you to use that power property for logarithms to bring them down. Now, what's the natural log of e? 1. And if you remember that, we can begin to skip a step. So that's 2k. Divide by 2, you're going to need a calculator. Okay, so take ln2 and divide that by 2. And you're going to want to go pretty far with these, because the farther you go, the more accurate it is. So I'm now going to have y equals 2e to the 0.3467 power.
Okay, how much can we simplify that?
What do you mean?
Like, can we just put 3.5 or 0.35?
No, you're going to want to go, and watch this, guys. If you have a graphing calculator, let me show you a cool feature, because like on your paper, you might say 0.35, but when you're doing the computation, don't do that. And let me show you something, okay? This will be super cool. All right, can you guys do this with me? If you do ln2, make sure you divide, or close that parenthesis, sorry, divide by 2. Now I'm going to show you a cool feature if you didn't know this already. On your graphing calculator, there is this button. It's one above the on, and it's STO. And that's called the store key. Okay, do you guys see that? One above the on is STO. We're going to do store and put it in X. Okay? Now watch this. Okay? I'm going to go back to my slide a moment. Because when I want to do this, if I want to do this when it says, what's the value of y when t is 3? Watch this, okay? So that if you want to then shorten what you're writing, but we're not going to skimp on the actual number, watch this. What's the daisy? There it was. Okay, so I'm going to take 2e, and then I'm going to press the X key that I stored it in. Isn't that fantastic?
So we have to do times 3.
Yeah, you're right. Sorry. Where was that? Times 3. Sorry. Yeah. Whoops.
So do we just do 3x?
Yeah, 3x. Sorry. Times 3. Whoops. So I'm like, that's not the right answer. There. It should be 5.657. So let's and we'll practice it today. We're going to do this store feature. So then I don't care how far you write it on the body of your work, provided you are using the store feature and going as far as the calculator will go. Because here's the problem. When you start talking about like millions and millions of whatever it is, like whether it's cells or dollars, if you cut off in the 10th place versus going out 6, 7 decimals, you will get a vastly different answer. And so I heard about this. This was many years ago now, but one of the people working for NASA, that they were trying to send something like a satellite out, and they rounded, like I think to the 10,000th place instead of going further, and the satellite missed its target by like 100 miles. Like it was really bad. So, you know, when you talk about this, it does depend on what you're doing and how far you need to go. Yeah.
So do we have to go back in and clear that out?
Or
you don't. Next time we store it.
Next time you store it, it'll change, and that's the only time you should press that button is when you want to use it again. Okay, it does have a note here. I don't know if you've ever done this, but I thought for funsies this would be good too. Is on your graphing calculator, you have what's called a exponential regression model. Okay, and we'll see how close we get to what we came up with. Okay, on your calculator, on the graphing calculator, if you press stat, okay, press the stat key. And I don't know if you knew you could do this. On number 1, press enter. Okay, on stat, number 1, press enter. Then you want to arrow up to the tippy top and press clear, enter. And it's going to delete if there's anything in there. If you have nothing there, just wait for me. Again, go to the tippy top, press clear, and enter. And here's the deal. We had 2 points. We had 0, 2, and 2, 4. So you're going to write it like this. 0, and then the 2 I'm using is the 2 from the t. So I'm doing my t's first, and then you go to the right, and you do 2 and 4. So like this would be either your x's and then your y's, or our t's and our y's, okay? Okay, so you, again, press stat. On edit, press enter. You get to the tippy top, press clear. Do not press delete because it'll delete the list and I'll have to fix it. You'll get an error. All right, now what I want you to do is press second and mode. That's the second quit. And you press stat. Okay, press stat again, but you have to be back on the home screen. Arrow to calc. And you can actually do this with any set of data. If you have data and you think it's going to be a parabola, you can do a quadratic regression. If you think it looks like a cubic, like an x cubed, if you think it's a quartic, x to the 4th, this is a line. If you go down now to, keep going. There's a logarithmic, but the 0 should be exponential regression. You press enter and enter. If you have a newer calculator, it might have all this stuff on your screen. Just press enter through it until it spits this out. Yeah, Christian?
I'm just as curious to, couldn't we have stored it inside one of the alpha letters?
You could use any letter you want, yes.
Oh.
You actually could. So do you see this is y equals a times b to the x, so it's 2 times 1.414 to the x power is another possibility. But that's not using calculus, okay? All right, flip the page when you're ready. And there's a note at the top of this page. It says, radioactive decay is measured in terms of half-life, the number of years required for half of the atoms in a sample of radioactive material to decay. The rate of decay is proportional to the amount present. Some common half-lives of radioactive isotopes are listed on page 417 in your textbook. Example 3, suppose 10 grams of the plutonium isotope 239 was released in the Chernobyl nuclear accident. How long will it take for the 10 grams to decay to 1 gram? So here's the deal. In that note above, half-life, okay, that rate of decay is proportional to the amount present. So what that means is you're going to start with y equals CE to the KT power. Now something that's inferred, and I want to be explicit with you, what's inferred is when they tell you the initial amount, that time is 0. So it says you start with 10 grams. So that means at no time, okay, at 0 time, you have 10 grams. So what we're going to do is we're going to plug in. And are you okay with e to the 0 is 1, so c is 10. So I now have y equals 10e to the kt power. Now something else that's inferred about half-life. If I start with 10 grams, how much would half be? 5 grams, okay? So let's think about this. I would end up with 5 grams, but the half-life, oops, I think we need to open your books to page 417.
It's 24,100. I went and checked.
Thank you. That is correct. Thank you. It is 24,100. That's the time it takes to cut it in half. So 5 equals 10e to the 24,100k. So now we need to find the k value. So we'll divide by 10. That's 1/2 or 0.5. And this is going to be one of those cases. K is going to be itty bitty. It's going to be a teeny tiny number, and we're going to want, you're going to be forced to use the store feature, whether you want to or not. So don't sit there and say, I'm not doing it. You need to do it because it's going to be so small. So now we're going to take the natural log of both sides, but are you guys comfortable? If I take the natural log of e to a power, it's going to end up being the power because ln cancels every time. So this is just 24,100k. And to solve for k, I'm going to pull my calculator up and then store it. So this is going to be ln 0.5. Make sure you do close your parenthesis. Divided by 24,100. And are you getting this number and do you understand what it means? Negative 2.876 e negative 5. That's scientific notation on the graphing calculator. It means times 10 to the negative 5th. So that's negative 0.0000, 4 zeros, then the 2. Okay? So I'm going to store x. And what Christian mentioned a moment ago is you can actually store it in any letter you want. It's just a less keystroke to make x. Like you could say alpha A, but then you're going to always have to bring up alpha A. So it's kind of a pain to pick a different letter. All right, so on my paper, though, I'm going to put the negative 0.0002876. 7. You can, do whatever you want on here as long as you're, using the store feature. So this is now y equals 10e, and here's what you could do. Because, I really don't want to write that again. On your paper, do this. Do store x, and you could write it like that and avoid it. Do you see that? If you just tell me you stored it, use whatever letter, okay? As long as that's not confusing. Then it says, how long will it take 10 grams to decay to 1 gram? So now I finally got to the question. How long will it take the 10 grams initially to decay to 1 gram? So that's 1 equals 10e to the xt power. If I divide by 10, that's 0.1 equals e. Now remember, this x, and this is where, maybe you do want to use a different letter, call it b or a or something, because you don't want to think it's a variable, okay? So I'm going to do ln 0.1, and we're going to divide it by the stored x. So on my calculator, that's ln 0.1 divided by x, and you should be getting 80,058.5.
And that's t.
That's the time. That's ridiculous, isn't it?
Wait, should we be solving for it?
It says find the time, so we found t.
Mine's giving me some weird 9.8.
Did you find k first? The k was negative 0.0000287761.
Yeah, I did. And I stored it inside alpha A, which I'm using.
So did you do ln 0.1 divided by your alpha a?
Do you graph digger?
I do, actually.
Okay.
You got it now?
That was my error.
Okay. All right, let's try example 4. Suppose an experimental population of fruit flies increases according to the law of exponential growth. So that means you immediately write down y equals CE to the KT tower.
In physics. No. We have to book that and it's all that.
Now, it says there were 100 flies after the second day of the experiment and 300 flies after the 4th day. All right, so this time they didn't give us the initial amount. Do you understand that? So that's going to be a bummer, and we need to figure it out. On day 2, there's 100, and on day 4, there's 300. So let's see what we can do with that. So if I plug in 100 equals CE to the 2K, and so I don't know what to do with that. I've got 300 equals CE to the 4K. All right, so bummer. I have 2 letters in 2 equations. Unfortunately, trying to add them or subtract them won't get rid of anything because these are not like terms. But watch what I can do instead. I'm going to take the 300 equals CE to the 4K, and I'm going to divide the 2 equations. Watch this. This is cool. If I divide the 2 equations, 300 divided by 100 is 3. Do you see the C's cancel? The C's actually cancel. And then, let's think about exponent properties. A to the m over a to the n is a to the m minus n power. So e to the 4k divided by e to the 2k, you would subtract the exponents, so it's 2k. Now I can take the natural log of both sides. So take the natural log of 3 and divide by 2, and you're going to store this number, okay? So let me grab I'm getting 0.5493-ish. ln 3 divided by 2, store that in Oops, whoops, that's not right. Okay, wait. ln 3 divided by 2, there we go. Store x. Okay, so now this is y equals CE to the 0.5493 t power, but I've stored it. Now I don't know C. Okay, I don't have C yet. I can take either of the two original points I have. There's a T and a Y. If I plug in the T and the Y, I can find C. So this is 100 equals CE to the 0.5493 power times 2. All right, so on my calculator, let me show you how you do that. This will be 100 divided by e to the x times 2. And you should be getting 33.3 repeating.
For basically 1/3.
Yeah. So I'm just going to go a couple of spots. So this is y equals 33.33 e to the 0.5493 t power.
Oh, we're not on this fraction. Can we use the line?
Yeah, you could use the line. It says, but okay, wait a minute. The question says approximately how many flies were in the original population. We're not going to say 33.3, are we?
Maybe.
No, you would say there were 33 flies. You see C is the initial amount. All right, let's try to get to example 5, and then we'll stop. Declining sales. So we've seen radioactive decay, population, and now in business calculus, there is business calculus, they use this sort of stuff. It says, 4 months after it stops advertising, a manufacturing company notices that its sales have dropped from 100,000 units per month to 80,000 units per month. Let's pause right there because there's a whole lot in there. It says 4 months after it stopped, it went from 100,000 to 80,000. What would be my 2 ordered pairs I gained from that? 0, comma what? It started with 100,000. 4, comma nice. All right, here we go. I want to give you a head start. Find, this is just like example 3. Okay, this is like example 3. I do have an initial amount. I want you to find C and K. Okay, try to come up with the original equation because I think you can. I think you can.
Stop it. You're going. How party?
Yeah. Like a lot of other teachers.
I'm not doing it. She's just gonna explain it anyway.
A lot of 20 days.
Karen's a good student. I want to be like her, but I feel like that.
Same meeting. You can't be distracted. See, look at that freaking time.
You're gonna have to help me too.
I'm gonna have to learn myself a fucking.
You're gonna have to help me.
I'll make a bed and bug and get.
Bed and bug. Should make a bed and bug.
We're gonna have to like make bets. So if I get home, I'll bring you.
I have really no idea what we're doing.
You do.
I don't.
You do. You just don't.
Oh, I never don't.
Okay, so look.
I just know there's some water so we cool off. So hot.
You can put it in store.
Yes.
Wait, where does
You can
Y
store
come from?
any letter.
This is Y right here.
I'm gonna start doing like Z.
So look, okay, for those of you that are struggling to get started, you take anything that has the 0, if that's an option, we want to start with that. Okay, so plug it into this. 100,000 equals C times e to the k times 0. E to the 0 is 1, so there's my initial amount. Now they gave you a second point that we can find the k value by plugging in the y and the t. So we're going to go 80,000 equals 100,000 e to the k times 4 power.
Carol. Oh. I thought you were right there. I listened hello. Take you back. Dude, text me out. I'm going to take the best nap next to you. I don't know. She saw it.
Okay, so what are you guys getting for k?
-0.055785.
Yes, good job. Okay, so k is about to approximate it on my board. So I'm getting y equals 100,000 e to the -0.0558 t. Then it says, if the sales follow an exponential pattern of decline, what will they be after another 2 months?
So you plug in 2.
You plug in 6. Because it's already been 4 months, and so good catch here. So we're going to do y equals 100,000 e to the -0.0558 times 6. And let me pop this in on my calculator, though. Where's my calculator? Here it is. So we have natural log of 0.8 divided, natural log of 0.8 divided by, what was it divided by? 4. Store that for x. Then I have 100,000 e to the x times 6 power. Are you guys getting 71,554? And this is units, so you can't make a partial unit like if you're manufacturing. You're not going to run your machine part way. So 71,554. Now, I want you guys to look through the stack of papers that you have. And you should have one that says 6.2 worksheet number 1. And I need to double check. Number 5, the half-life of that plutonium is the 24,100. Did I give you that or not give that to you?
4,100. I'll remember that.
Yeah, okay, now, 24,100. On here, we did not get to, you can't do 8 or 9, but everything else is due Monday. Okay, circle 8 and 9, you can't do those yet because I didn't get to Newton's law of cooling. But you can do 10, 11, and 12. You know how to do that. Okay, by Monday, this is due Monday. 6.2 worksheet number 1. You'll notice in the packet of stuff, Monday we're going to do classwork for 6.2, and then we'll finish the notes, and then you'll have the 6.2 worksheet 2 plus 8 and 9. Okay.